a balanced three-phase system, the neutral current is ideally zero because the currents in the three phases sum to zero. However, when the loads in the three phases are not equal, the system becomes unbalanced and a current flows through the neutral conductor. The magnitude of this neutral current depends on the degree of imbalance. Consider a scenario where a two-pole breaker in a three-phase panel feeds an appliance rated at 50 amps. This appliance is connected line to line using phases A and B. A neutral wire is also run to the appliance, but for this specific load, the calculated load on the branch circuit neutral is 0. However, the calculated load for the panel feeder neutral is 50 amps. This occurs because the 50 amp load is only connected between phases A and B, and is not equally distributed across all three phases. The neutral carries the unbalanced current between phases A and B. In a balanced three-phase system, the neutral current is 0. However, in an unbalanced system, the neutral current can be significant. In the example you gave, the load on phase A is 50 amps, and the load on phase B is 0 amps. This means that the unbalanced current is 50 amps which flows through the neutral. The panel feeder neutral is sized to carry the maximum unbalanced current that can occur in the system. In this case, the maximum unbalanced current is 50 amps, so the panel feeder neutral is sized for 50 amps. The branch circuit neutral is sized to carry the maximum neutral current that can occur in the branch circuit. In this case, the maximum neutral current is 0 amps, so the branch circuit neutral is sized for 0 amps. It is important to note that the neutral conductor is not a current-carrying conductor in a balanced three-phase system. However, in an unbalanced system, the neutral conductor can carry significant current. Therefore, it is important to size the neutral conductor appropriately to ensure that it can safely carry the maximum unbalanced current that can occur in the system. To further illustrate, let's analyze the current flow. Since the appliance is only connected to phases A and B, phase C has no load. Assuming a balanced voltage source, the current in phase A is 50 amps, the current in phase B is 50 amps in the opposite direction, and the current in phase C is 0 amps. The neutral conductor provides a return path for the unbalanced current, ensuring that the current flow is balanced at the source. In this specific scenario, the neutral current is equal to the current in either phase A or phase B, which is 50 amps. The panel feeder neutral must be sized to handle this 50 amp neutral current to prevent overheating and ensure safe operation. The branch circuit neutral, in this case, carries no current because the load itself is connected line to line. It doesn't utilize the neutral connection to operate, and the connection is purely for other operational functionality that is out of scope. Therefore, the neutral current within the branch circuit is 0. However, the panel feeder neutral sees the cumulative effect of all unbalanced loads connected to the panel. It's essential to understand that the panel feeder neutral must be sized based on the potential maximum unbalanced load within the entire panel, according to the National Electrical Code, section 220.61. This section outlines the requirements for calculating the neutral load in a service or feeder. The calculation of neutral load involves considering the types of loads connected, such as lighting, receptacles, and appliances. For household ranges and similar appliances, specific demand factors are applied to reduce the calculated neutral load. These demand factors recognize that not all appliances will operate at their maximum rated load simultaneously. However, for nonlinear loads, such as those produced by electronic devices like computers and LED lighting, the neutral current can be significantly higher than the phase currents due to the presence of harmonic currents. In these cases, the neutral conductor may need to be sized larger than the phase conductors to accommodate the increased current. The National Electrical Code provides guidance on sizing neutral conductors for nonlinear loads in section 220.61c. This section requires that the neutral conductor be sized to carry the maximum unbalanced load, including any harmonic currents. When designing a three-phase system, it is crucial to minimize imbalances between phases. This can be achieved by distributing loads evenly across all three phases. By doing so, the neutral current is reduced, and the overall efficiency of the system is improved. Additionally, balancing the loads helps to prevent voltage imbalances, which can negatively affect the performance of equipment connected to the system. One practical approach to balancing loads is to divide lighting circuits, receptacle circuits, and appliance circuits equally among the three phases. For example, in a commercial building with multiple lighting circuits, each circuit can be connected to a different phase. This ensures that the total load on each phase is approximately the same. Similarly, when installing receptacles, they can be wired to different phases in an alternating pattern. This helps to distribute the load evenly throughout the building. Another consideration is the use of single-phase and three-phase equipment. Single-phase loads contribute to imbalances, while three-phase loads typically draw balanced current from all three phases. Therefore, whenever possible, it is preferable to use three-phase equipment. For example, instead of using multiple single-phase air conditioning units, a single three-phase unit can be installed. This reduces the overall imbalance in the system. Furthermore, regular monitoring of phase currents can help identify potential imbalances. By measuring the current in each phase, it is possible to detect if one phase is significantly more loaded than the others. If an imbalance is detected, corrective actions can be taken to redistribute the loads. This might involve moving circuits from one phase to another or adding additional circuits to the less loaded phases. In addition to balancing loads, proper grounding is essential for ensuring the safety and reliability of a three-phase system. The grounding system provides a low-impedance path for fault currents, allowing protective devices to quickly clear faults and prevent electrical hazards. The grounding electrode system typically consists of a grounding electrode, such as a ground rod or a metal water pipe, connected to the neutral conductor at the service entrance. This connection ensures that the neutral conductor is at or near ground potential. The size of the grounding conductor is determined by the size of the service entrance conductors, as specified in the National Electrical Code Table 250.66. The grounding conductor must be large enough to safely carry the maximum fault current that could occur in the system. Additionally, all metal enclosures, such as electrical panels, equipment housings, and conduit, must be bonded together and connected to the grounding system. This ensures that all exposed metal parts are at the same potential, reducing the risk of electric shock. The importance of proper neutral conductor sizing cannot be overstated. An undersized neutral conductor can overheat, leading to insulation damage, fire hazards, and even system failure. The neutral conductor carries the unbalanced current in a three-phase system, and if it is not sized appropriately, it can become overloaded. Overloading can cause the conductor to heat up, which increases its resistance and further reduces its current carrying capacity. This can create a cascading effect, leading to a thermal runaway and potentially causing a fire. To prevent these hazards, it is essential to follow the National Electrical Code guidelines for sizing neutral conductors. The code provides specific requirements for calculating the neutral load and selecting the appropriate conductor size. These requirements take into account the types of loads connected, the presence of nonlinear loads, and the potential for future expansion. In addition to proper sizing, it is also important to ensure that the neutral conductor is properly installed. This includes making sure that all connections are tight and secure, and that the conductor is protected from physical damage. Loose connections can create hot spots, which can lead to overheating and potential fire hazards. Additionally, the neutral conductor should be protected from abrasion, corrosion, and other forms of damage. The National Electrical Code also addresses the issue of neutral current in shared neutral conductors. In multi-wire branch circuits, a single neutral conductor is shared by multiple circuits. This can be an efficient way to reduce the number of conductors required, but it also increases the potential for neutral overload. If the loads on the shared neutral conductor are not balanced, the neutral current can exceed the ampacity of the conductor, leading to overheating and potential hazard. To prevent neutral overload in shared neutral conductors, the National Electrical Code requires that the circuits sharing the neutral conductor be connected to different phases. This ensures that the currents in the different circuits tend to cancel each other out, reducing the overall neutral current. Additionally, the code requires that the shared neutral conductor be sized to carry the maximum unbalanced load that could occur in the system. In conclusion, understanding the behavior of neutral current and unbalanced three-phase systems is essential for ensuring the safety and reliability of electrical installations. By balancing loads, properly sizing neutral conductors, and following the guidelines of the National Electrical Code, it is possible to minimize neutral current and prevent potential hazards. Additionally, regular monitoring of phase currents and proper grounding practices can help identify and address potential imbalances before they lead to problems. By taking these steps, you can ensure that your three-phase system operates safely and efficiently for many years to come.